am with a second lesson on topic 2.1. We covered the basics of classification last time. This time we're going to move on to look at the evidence we use to classify organisms. Now, I'm going to start with a quick game of odd one out for you. 3 questions in each one. I'll give you 3 names of 3 animals. You state which is the odd one out. Pause the video after each question if you need to. Right, question 1. A dolphin, a shark and an elephant. Should be nice and easy. Question 2. An owl, a bat and a gorilla. Question 3. A seal, a penguin or a pigeon. Right. Answers to those, by the way. Question 1. Dolphin, shark, elephant. Dead easy, isn't it? Of course, the odd one out is the elephant, isn't it? Completely different to the other 2? Well, no, it's not. Actually, when I talk it in classification terms, the shark is the odd one out. The other 2 are mammals. Question 2. An owl, a bat and a gorilla. Surely it's the big hulking gorilla that's the odd one out. The other 2 fly around at night. Well, again, you're wrong if you put the gorilla, you're fools. The owl is the odd one out. The other 2 are mammals. An owl is a bird. Third one, seal, penguin, pigeon. Same pattern. If you put the pigeon as the odd one out, you're a complete and utter fool. The pigeon and the penguin are both birds. The seal, being a mammal, is the odd one out. Right, so here's a little chart showing the 5 classes of vertebrates. See them clearly enough for yourselves. The question is, what evidence do we use to put all these animals, for example, which look totally different, many of them, what evidence do we use to put all of these in the same class? And on the other hand, we decide that all of these belong in a different class. Same for the others. Well, let's have a good look at exactly that. What is the evidence that we use? Let's begin by actually discussing what we do not use, which is external appearances. If we were, we'd probably class the shark, the penguin and the dolphin very closely together in our classification system, when actually they are all in different classes, as you can see there. Why are they in different classes is the question. The answer comes from looking at their internal rather than external structure. You can see there the internal skeleton of the fin, the wing and the flipper are completely different from each other. So looking at internal structures is more useful than looking at external structures. Now, the shark fin, the penguin's wing and the dolphin's flipper are examples of what we call analogous structures. Structures which have similar appearances, similar functions as well, but different structures. And analogous structures can be misleading when it comes to classification. As I said earlier, it can lead us to falsely think that 2 different species are closely related because of the similarities in their structures, when in fact they are not. And the presence of analogous structures is why we do not use external appearances as the basis of classification systems. What we can use as the basis for classification is what we call homologous structure. Here are some examples of 3 homologous structures. The human hand, a dog foreleg, or a whale's flipper. As you can see, they're all based around what's often called the pentadactyl limb. Pentadactyl, as they all have 5 digits on the ends. And from this you can see that, a human arm, a dog leg, and a whale's flipper, whilst rather different in appearance, especially the whale's flipper, actually have similar internal structures, suggesting that all 3 have a common ancestor in the distant past, whereas a bird's wing is not based around the same sort of pentadactyl structure. There are not 5 digits there, suggesting that birds are more distantly sort of related to these 3 organisms than the other 3 are to each other, and therefore birds should be in a different class. However, basing classification systems on internal structures, whilst internal structures can be useful guides, trouble is they lack full precision. It's very hard to make definite decisions on organisms which are pretty similar in their internal structure and decide, which ones are more closely related to each other. Even on this, you can say, well, human, dog, whale, which one of these 3 is the odd one out? Which one is more different to the other 2? Can be it's not fully precise, it's slightly subjective. Therefore, being scientists, what we like is greater precision, some actual figures that we can use on which to base our classification systems. So, where do we get such evidence? Well, one possibility is from what's called DNA profiling or DNA fingerprinting sometimes, using a technique called electrophoresis, by which we analyse the DNA of different organisms and see how similar that is. Now, at this point, I want you to pause my video and watch the 3 videos that I've sent you on electrophoresis, just during the specified time intervals. Come back to me when you're done with those. Right, now as you've hopefully learned, electrophoresis involves at first using something called restriction enzymes to cut up the DNA of different organisms into sections. Now those enzymes might cut the DNA after certain specific sequences. Let's just say, for the sake of argument, the enzyme actually cuts the DNA after every time you get GGG in a row. In reality, it's a bit more complex than just cutting it every triplet. But let's use it as a good example. Let's just say this enzyme could cut the DNA after every GGG, and you were analysing the DNA of these 3 organisms. What would happen after it had been cut up by an enzyme? Right, this is what organism 1 would look like. There would be a section cut up at that point, and 2nd section at this point, 3rd one there, 4th one there. So on the electrophoresis plate, you would get 4 different bands corresponding to these 4 different sections. Now, species 2 doesn't have a GGG there, so its 2nd section would be much longer than that for species 1. Does have another GGG there, so would have 4 different bands, but they're of different lengths to those of species 1. Now, species 3, pretty similar to species 1. All 3 of them have the same initial length cut there, but species 3 would have the same 2nd band as well. even the same third band, but its fourth band would be slightly different. So what you would find is, for species 3, 3 of the 4 bands would match that of species 1. With species 2, only one of its 4 bands would match that of species 1, and you would conclude from this that species 1 and 3 are the most closely related, therefore have the more recent common ancestor. Now, that's DNA profiling. Let me emphasize that this is not the same as DNA sequencing. By carrying out electrophoresis, it does not allow you to find out the exact sequences of bases on the DNA. Right, this is all you get as the actual result of electrophoresis, a number of bands like that. But whilst it is not quite as precise as getting a full DNA sequence, you're not getting out something like this, it does at least give you a result that is sort of simple to interpret, and allows you to, for example, compare species 2, 3 and 4 here with a common ancestor 1 and say, well, species 3 is the most closely related to that. Just a quick, easy visual result to interpret. So that's electrophoresis of DNA. Now, however, if you can get a full DNA sequence of different species, that, of course, can give you even more valuable information. At this point, again, pause my video and watch the next 2 videos I've sent you on DNA sequencing and also protein sequencing, which are the other 2 methods we use to compare evolutionary relationships and therefore work out classification systems. Right, now when we look at phylogenetic trees like this, and let me again remind you, you could, for example, say from this that a chimp is more closely related to a human than it is to an old world monkey because it has shares a more recent common ancestor with a human. What you could say is, how do we know a chimp is more closely related to a human? Well, to some extent we can use fossil evidence to find common ancestors, but fossils, of course, are notoriously difficult to find. It's been estimated, by the way, that only 1% of species that have ever lived on the earth have ever left fossils. That's 1% of species have left even a fossil of a single member. So fossils are few and far between and hard to find. And whilst they have provided us with quite a lot of valuable evidence, there is something called proconsul, which has been found. Fossils of a creature called proconsul, which is thought to be a common ancestor of humans and chimps, has been found. It's very hard to piece together full evolutionary pictures from fossil evidence alone, which is why DNA sequencing has been such a valuable tool since it was invented. As you've hopefully learned from watching the video I sent you, that DNA sequencing works in a relatively simple way, really. If you can work out the entire sort of DNA sequencing, you wouldn't necessarily use the entire genome, but a section of DNA, often just a single gene that, say, codes for a single protein in all these different animals, you could use that DNA sequence to work out evolutionary and therefore classification relationships. The more bases species have in common, the more closely related they are and the more recent their common ancestor lived. Even from just a brief examination of this sequence, you can see that on this gene, the ostrich, emu and the turkey have a longer sequence than the other 4 species. They have an extra triplet at this position, immediately suggesting these 3 are more closely related to each other than they are to those. And you can again then see the differences here. These 4, the mammals, of course, fairly similar at this position, whereas the 3 birds are totally different. Notice how the horse and the donkey are identical at this position. The others aren't, suggesting these two are more closely related to each other than those. Now, however, in reality, you get a sequence of bases thousands of bases long. You would use a computer to analyse it and tell you the number of differences between each of these species. And the greater the number of differences, the less closely related they are. Now, given that DNA codes for proteins, as you've already learned, an alternative using DNA sequencing is just to use the amino acid sequences in different proteins. For example, a section of hemoglobin in certain different species is shown here, and you can immediately see, even just from the first amino acid, it suggests humans, chimps and gorillas are more closely related to each other than they are to these other creatures. Now, you can use DNA sequencing, you can use amino acid sequencing. Given that the DNA only codes for amino acids anyway, you might at first think you can use either one interchangeably and they're both equally as valuable. Actually, that's not quite true. Can you pause this video for a second and just think to yourself, which of the two is more valuable, more precise, and be able to give us more precise information about sort of the relatedness of two different species? DNA sequencing or protein sequencing? If you're a bit stuck, I'll just remind you of this chart. This is the genetic code showing you which triplets of bases code for which amino acids. If you weren't sure, think about this chart and then make your decision. Right, the answer is DNA sequencing is more valuable. Protein sequencing is very valuable, tells us a lot of useful information. DNA is even better though, simply because if species 1 had UCU as its first triplet, species 2 had UCC, they've actually got a different triple, got a difference in bases of 1. There is 1 difference in their base sequence already. But if you were just analysing their amino acid sequence, you'd just see serine, and you would not have been able to pick out the fact that there is actually 1 difference in their base sequencing. So because of this, the fact that more than 1 triplet can code for a single amino acid, DNA sequencing is even more valuable than amino acid sequencing. Right, as I've mentioned in my email, you should now be able to go on and make further progress on the topic 2.1 work, complete all of page 2 of the note sheet and even the first part of page 3 up to the end of this bit I'm showing you here, how DNA and protein sequencing can be used to assess evolutionary relationships. Do not go on to the biodiversity part until next week. Then you can also go on and do section C on the question sheet and also the homeworks I've asked you to do on the email. Okay, how about finishing as we started? Another game of odd one out for you all. Right, question 1. Human, dog, lizard. Question 2. Human, dog, kangaroo. 3. Dog, cat, seal. Question 4. Gorilla, monkey, or human. And question 5. Me, a gorilla, or a chimpanzee. Right, question 1 should have been easy. Human, dog, lizard. The other one out is, of course, a lizard, being a reptile. The other 2 mammals. Now, question 2, human, dog, or kangaroo. All 3 mammals this time, but as illustrated on this chart, marsupials are very primitive mammals. Kangaroo, of course, being a marsupial, and their much more distantly related to placental mammals such as dogs or humans. The odd one out is the kangaroo. They're primitive, by the way, because they don't give birth to sort of reasonably well developed young. They're young are given sort of birth to when they're really only half developed, and that's why they have to be kept in a pouch. So number 2, kangaroo, the odd one out. Number 3, the dog, the seal, and the cat. Now, actually, the answer is a cat to that one. Seals and dogs are much more closely related to each other. As I mentioned before, you just look at the head of a seal and a dog, and they look remarkably similar, actually. If you weren't inclined to believe me, just have a good look at that, and it will emphasise the point. So the cat is the odd one out there. Question 4, the gorilla, the monkey, or the human. Us humans are sometimes quite vain and like to think ourselves as being really distinct and different to all the other species. And, gorillas are just big monkeys, really, aren't they? And we're totally different to them, and therefore we must be the odd one out because we're more special. No, you can see clearly from this chart, a gorilla is much more closely related to a human than it is to the monkey, and it's the monkey that's the odd one out. Question 5, me. Believe it or not, I am a human, by the way. Me, a gorilla, or a chimp. Shame on any of you who've written down the chimp is the odd one out because I resemble a gorilla. The answer, you might again have been tempted to put humans as the odd one out. Gorillas and chimps, just big hairy apes, aren't they? Quite similar to each other. We're totally different. Again, look at that. The chimp is really the key to it. The chimp's in the middle here. Which is a chimp more closely related to, a human or a gorilla? It's more closely related to a human than it is to a gorilla. The odd one out was the gorilla. Okay, that will do for today. I'll try to give you one more video next week on the remainder of this topic. Bye for now.